The given question is a steady current I flows along an infinitely long hollow cylindrical conductor of radius capital R. This cylinder is placed coaxially inside an infinite solenoid of radius 2R. The solenoid has n turns per unit length and carries a steady current capital I. Consider a point P at a distance small r from the common axis. The correct statements are, so these are the statements. Okay, four statements here given. Statement A, B, C, and D, and we have to check which of the statements are the correct. So let me first give you a brief about the magnetic field. Okay, and see, in all the four statements we have to check the magnetic fields. Okay, so let me give you a brief about the magnetic field created by a hollow cylindrical conductor and a solenoid. Okay, so first of all, let's say we have a hollow conductor like this. Okay, in which a current is flowing. Okay, and current always flows through the circumference. Okay, let's say I current is flowing, okay, through this hollow conductor. So let this be the axis of the conductor. Now if I take a loop, okay, if I take a loop inside this conductor, then according to the Ampere's circuital law, then according to the Ampere's circuital law, in this loop, if I take the line integral of the magnetic field, then it will come out to be equal to mu naught times the current passing through this loop. So current passing through this loop will be 0, hence magnetic field setup would be 0. And if I take a loop outside this conductor at a distance small r, okay, then according to the Ampere circuital law, it will be B dot dl, and this will be equal to mu naught times I. And from here, after doing the calculations, we can see that the magnetic field at this distance r we can find equals to mu naught I divided by 2r. Okay, so and the for the direction we have to use right hand thumb rule. Okay, so we have to place the thumb in the direction of current and the curl of finger will give the direction of magnetic field. So if we place thumb in the direction from left to right, then this will be the polarity of the magnetic field. Okay, dot from the above and cross from the below. So this is about the hollow cylinder. Next we have is a solenoid. Okay, so for a solenoid, basically we have, let's say this is a solenoid. Okay, this is a solenoid on which the wire is wound. Okay, the wire is wound like this, and we know that for a solenoid, let's say I current is flowing inside the solenoid wires. Okay, so we know that the magnetic field generally confined within the solenoid like this. Okay, and we can find the direction of this magnetic field by the right hand thumb rule, and it will be along this direction. Okay, so this will be the magnetic field, and magnetic field outside the solenoid is always 0. Okay, magnetic field inside only, magnetic field stays confined within the solenoid only. Okay, and it is given as B equals to mu naught times Ni. Okay, where I is the current flowing through the solenoid wire, N is the number of turns per unit length, and mu naught is the magnetic permeability of free space. So now let us check the statements one by one. So we are having in the region 0 to R, then less than capital R, the magnetic field is non-zero. Okay, so let me draw the figure for this end also. So we are having a solenoid. Okay, we are having a solenoid like this, inside which a hollow cylinder is placed. Okay, inside which a hollow cylinder is placed. Let me make it with other ink. So this is the hollow cylinder which is placed inside the solenoid with a common axis. Okay, so this is the common axis, and they are both infinitely long. Okay, they both are infinitely long. the solenoid as well as the hollow cylinder. Okay, so let me wound the wire. Okay, so like this, wire is being wound on the solenoid. So I'm taking just few turns just to show the magnetic field. Okay, I current is flowing in the solenoid as well as I current is flowing in the hollow cylindrical conductor. So now we are given R, capital R is the radius of the hollow cylinder and 2R is the radius of the solenoid. Okay, so now in the statement 1 we are given in the region 0 to R less than capital R the magnetic field is non-zero. So let us check this. So it is saying about this region. Okay, let's say we have a point between R. Okay, for statement A we are having a point between 0 to capital R the magnetic field is non-zero. Now see, inside the due to the hollow conductor inside this portion the magnetic field due to this hollow conductor will be zero, but due to the solenoid there will be magnetic field present because all the magnetic field due to solenoid will be confined within the solenoid only. Hence the magnetic field inside this region 0 to R to capital R will be non-zero due to solenoid. Okay, due to solenoid, right? So the given statement 1 is correct. In statement B we are having in the region R from small r capital R to R the magnetic field is along the common axis. Okay, now see, in for this part we are having here this is the point. So here we can see that due to this hollow conductor at this point. Okay, let me show this point here. So let's say this point is P. Okay, so due to the hollow conductor the magnetic field at this point would be dot polarity. It will be coming out of the plane or the screen, and due to the solenoid it would be along right direction, right? So we can say that the magnetic field will not be along the common axis because their resultant field would be somewhat cross magnetizing. Okay, and it will be not along the common axis. Hence the given statement B is false. In statement C we have in the region R less than 2 capital R the magnetic field is tangential to the circle of radius R centered on the axis. Now see what is tangential. This is the part tangential. If I have taken only hollow cylindrical conductor, then this dot and cross is representing the tangential magnetic field. But in at the B point, we can see that the magnetic field will be somewhat cross. This will be the B net magnetic field will be cross magnetizing. Hence, it will be. We cannot say that this will be purely tangential to the circumference or the circle. Hence, statement C is also incorrect. In statement D, uh, we have the statement in the region R less than 2R, the magnetic field will be non-zero. So see, in this portion outside, okay, let me take this point P outside the solenoid. So due to solenoid at this point, the magnetic field would be zero. But as I already mentioned that due to the hollow conductor there will be some magnetic field present at point P. So for statement D we have for region R greater than 2R the magnetic field will be non-zero due to hollow cylindrical conductor. Okay, hollow cylindrical conductor. Thus the given statement D is also correct. Okay, given statement is also correct. So from the given four statements, statements A and D are the correct statements. Thank you.
Hello everyone. Let us start with our question. In this question, what is given? A cylindrical cavity of diameter A exists inside a cylinder of a diameter 2A as shown in the figure. So this is the this diameter is 2A, and here there is a cavity, this cylindrical cavity of diameter A. Now both the cylinder and the cavity are of infinitely long. So these are infinitely long. A uniform current density J flow through the length. Now if the magnitude of the magnetic field at point P is given as to be n by 12 mu naught Aj, we need to find the value of n. Okay. Now how can we do this? So for example, we can just replace this. We can say that this is our this whole cylinder, and let's say this is our cavity. So the net effect, if we need to find what is the net effect, what we should do, we should just say that here the current which is flowing is having a, we can just say that this is, we just say that current density, if here is J, so here it would be minus J. We can just put this value. Okay. Now, and this would be equivalent to this part. So due to this, let's say corresponding to this, current here is I and current here is I dash. Okay. So due to a long wire, what is the value of the this magnetic field at any point? So we need to find the magnetic field at this point at P. So we can say that its value would be equals to mu naught I divided by 2 pi. What is the distance from the center from here to here? It is equals to A. Then here the current density is negative, so magnetic field would be subtracted. So minus mu naught I dash divided by 2 pi. Now what would be the distance of this center to this part? So it would be A plus A by 2. That means 3A by 2 into 3A divided by 2. We can put it like this. Okay. Now, what we can write this as? Now I dash and I, what are the values in terms of current density? We say that I value would be equals to current density multiplied by area, because this current is current density multiplied by area. So here value would be equals to pi A square, and I dash value would be equals to current density, which is J, and what would be the area? Here radius is here radius would be A by 2. Okay, diameter is A, so radius would be A by 2. So area would be pi A square by 4. So here the area would be pi A square divided by 4. Now this is the magnetic field, net magnetic field, which we have written. Now if we substitute these values, and what we can take mu naught divided by 2 pi into A to be common. So our B net would then turn out to be mu naught divided by 2 pi A. If we take this value to be common, then here it would be I, and here it would be I dash divided by 3. So I value we just substitute, it is pi J into pi A square, then minus, here the value would turn out to be this J into pi A square divided by 4 multiplied by 3. So this 2 and this 2 would be cancelled. Now if we solve this, so our B net would then turn out to be mu naught J into pi into A square divided by 2 pi A. Okay, we can take these term to be common. We can take it to be outside. So there is a fact. So the factor here we have taken it to be common. So 2 pi we have already taken it to be common. So here this 2 we have, because we have taken 2 pi to be common, so we can take it to be common, and then 2 would be remaining here. So 2 would be remaining here. Okay, then here what will happen? So it would be 1 minus 1 divided by 6. It would be 1 minus 1 by 6. That means 5 by 6. So we can just write our B net would be then equals to mu naught J into this A divided by 6 into 2. That means 12. Then multiplied by 5. Okay. Now if we compare this, what is the here it is given n divided by 12 mu naught Aj. So if we compare this, so it would be n mu naught Ja divided by 12. So from here these value would be cancelled, so n value would turn out to be 5. So what is the correct answer? Correct answer for n would be equals to 5. Hope you have understood the solution. Thank you.